Thank you for joining the second part of my series on our energy future, which will be shown over two videos. Here we will be looking at emerging and new technologies to see how these can contribute to our energy transition. These emerging technologies provide the hope or opportunity to tackle climate change. So let me start with a summary of those technologies. Firstly, here are a number of developing energy supply technologies, ranging from new renewable energies through new nuclear, green hydrogen, blue hydrogen, and ammonia. Secondly, there are a number of developing energy use technologies, and this is where the consumer comes into the equation. We're looking at electric vehicles, heat pumps, hydrogen boilers, hydrogen fuel cells. We'll also look at insulation and public transport. Thirdly, we need a range of distribution and storage technologies. This is possibly the trickiest area for the regulator, and energy transition studies often inadequately consider this part of system change, which covers grids, both electricity and gas grids, looks at gas storage, looks at batteries, and district heating systems, etc. I will only provide a short summary of each of these technologies, as much more information is available on the web. But as you are aware, some technologies offer improved efficiency, while others provide more flexibility. These are two major themes, and they're shown here going through the different areas. Many technologies exist today. However, the real uncertainties are with scale up and deployment of those technologies. Ultimately, though, we must remember it's the consumer wants cheap, convenient, and now clean energy, the 3 C's. Let us start with the efficient electric technologies. Firstly, solar, wind, and batteries, now sometimes dubbed SWB. These charts from RethinkX and DMV well demonstrate the impact of scale and experience in SWB hardware. Costs have dropped dramatically, and that is why renewables have quickly become competitive to natural gas and other fuels for power generation. RethinkX go further and plot a future where over-installation of renewable capacity can compensate for the higher costs of battery storage. They go on to forecast that in the next 10 to 20 years, no gas-to-power plant will be viable, and they may well be correct. Based upon efficiency alone, it is uneconomic to convert renewable power to hydrogen to use in a fuel cell. However, as already discussed, this depends on how much flexible energy we will need in the future. We can well foresee renewable energy costs continuing to drop, but I would say that these cost trends do not take account of site impact and location costs, something I will pick up on later. We will see if our future is all electric. Hydro is an older renewable technology, and until recently provided more than half our global renewable energy resources. Here in Europe, Norway has benefited most from hydro, resulting in it being one of the leading electrified nations. Hydro projects provide opportunity for peak shaving demands and will work well with other renewables. Smaller schemes, such as this one in Canada, are now being considered. Hydro will certainly be part of our future energy, providing flexibility through expansion, though the expansion will be dependent upon suitable opportunities and guaranteed capacity values. Nuclear has long been the mainstay for the French electricity grid, and the UK has a number of aging plants which will be decommissioned over the coming decade. Germany is already decommissioning its plants based upon environmental concerns. However, nuclear provides a stable baseload and so again can work well with renewables. The UK has now a major new project under construction at Hinkley Point, but is also looking at developing small modular reactor technology. Safety and environmental concerns are being addressed, but the key will be cost. Given the drop in renewable costs, nuclear may be challenged to match those costs. though its baseload credentials will be an asset in our future electricity system. Expansion of renewables and/or nuclear will require further development of our power grids. The key factor, though, will be the origin of the additional supplies. Offshore wind farms will require expansion of coastal links, while more solar could help allow decentralization of our system. The loss of a key supply, such as happened in August 2019 in East Anglia, can lead to grid instability. Studies have indicated that full electrification could potentially require a tripling of our grid capacity. Decentralized power from solar farms and domestic schemes could reduce the need for this, but in turn it would still require enhanced grid coordination to ensure stable supplies to customers. Moving on to electricity consumers, let us look briefly at electrical vehicles, EVs, as they offer significant operating efficiency. The UK Committee for Climate Change notes that they are over twice as efficient as petrol cars, though this is only once all the power comes from renewable resources. As with renewables, though, Scandinavia is also leading the way with the take-up of battery electric vehicles. There is also a lot of research going on to improve battery and recharging technology. We are already seeing a breakthrough in electric vehicle sales, and improvements are being made with range limitations, recharging points, and recharging times. One of the key concerns, though, longer term, is the at-scale availability of materials for batteries. Replacement and recycling of old batteries and recharging all require improved standardization. The future is likely to be around smaller cars with more limited range and smaller batteries, as few round-trip journeys actually exceed, say, 200 miles. Heavy transport poses a greater problem for conversion, as here hydrogen vehicles and buses are being considered. Continuing with efficiency, let us next look at heat pumps. Tom Baxter of Glasgow University, in a recent presentation to the Institute of Chemical Engineers, noted heat pumps are a thermodynamic gift, and I certainly agree with him. The UK Committee for Climate Change are pinning their hopes on deployment of heat pumps throughout the UK's housing stock, some 22 million homes. As their chart shows, heat pumps offer between 200 and 400% efficiency gains against natural gas boilers, higher when compared to hydrogen boilers. Further, there is a big push to even out electricity demand across the day through smart meters, which can control the time of use of these pumps. However, today's energy cost differences, as already discussed, the economic case for consumers to adopt heat pumps has yet to be established. Heat pumps will become more cost-effective as fuel costs increase, though they come with very high upfront costs. Questions are being raised also as to whether heat pumps can work effectively in cold climates. Interestingly, as you can see here from the chart on the left, heat pump deployment is actually highest in Scandinavia. This is not surprising, for as discussed, Scandinavia has a greater dependence on electric power, and the energy efficiency gains from heat pumps makes sense there. However, in turn, from the chart on the right, you will also see that Scandinavian homes have some of the best insulation. The chart plots heat loss from the average home over an 8-hour period when it's 0 degrees C outside. As you can see, the UK has the worst performing housing stock in Europe with a 3-degree loss, compared to only about 1 degree loss for Scandinavian and German homes. The UK and continental Europe must significantly improve its insulation in millions of homes and premises. To counter this issue, the UK Committee for Climate Change are looking to deploy hybrid heat pumps, i.e. heat pumps with supplemental boilers. As we have seen, we can anticipate heat pump technologies will be deployed at scale. A precursor to any property converting to a heat pump will be that improved insulation. And as we have seen, the UK in particular is way behind the pace on efficient buildings. Major house refits can be accomplished at a cost, and this is being pursued in the Netherlands, and trials are taking place here in the UK. The UK's Committee for Climate Change has targets for house insulation, but I would question the capacity of the market to deliver this when we are still struggling with the post-Grenfell situation. Insulation of our buildings is critical for net zero, and more work is needed to economically upgrade our existing housing stock, as replacement is not viable in the time frame and far from carbon friendly. In any event, an insulation program will create hundreds of thousands of jobs, but we need the funding and a skilled workforce to deliver it.
Smart controls are another new technology critical for the wider deployment of electric technologies. Today, smart meters are being deployed to help suppliers manage supplies, and increasingly they will be used to help consumers schedule their purchases to off-peak periods. Smart controls will enable consumers to program their power usage to reduce costs. These are very relevant today while we have slack in our electricity supplies. Once we have wider rollout of these technologies and greater demand, the availability of low-cost off-peak supplies will drop. Acceleration of our power consumption will exacerbate the need for this technology, with the need to match demand to renewable power availability windows to reduce the need for batteries. Longer term, similar systems can be applied to our gas supplies. The next video in the series, Part 2B, will continue our discussion on new technologies, focusing on those associated with our flexibility vectors. I look forward to joining you there. Thank you.